All right. Good morning,
Okay.
everybody. Today, in our webinar series, we're the meshing. I'll try to give a quick review of the basics, and then I'll try to get in the newest features implemented in the latest version. So this should be useful for all levels. We're going to start with an introduction. Then I'll review the meshing parameters for both 2D and 3D. Then I will show the main defects we can find in the mesh and the main tools we have to address them and find them. After that, we'll show how to repair these defects with the available tools in Forge. And then we'll talk about the new tab, the Remeshing tab, and how to use it properly. Let's start with an introduction with the basics for meshing. As you know, creating a mesh is dividing the an initial domain, we can see it on the left, into a finite number of elements, we can see it on the right, using elements, okay, this type of elements. For curvatures, we are always going to have a small error to adapt to this geometry. We'll talk about it later. The solver will calculate the equations in each node. Okay, I think most of us know this, but again, I want to give a quick review for the basics. This is an example for the velocity field. The velocity field for this element, it's calculated using the velocity field in each node. There are different types of elements used in finite element analysis. Our software uses triangles for 2D and tetrahedrons for 3D. Okay, this is a question we get pretty often. We don't use the other elements at all. As you see, to discretize a geometry, we have infinite possibilities. We can choose an infinite number of meshes to discretize this geometry. I have some examples here. I'm trying to show that there's not a direct proportionality between the mesh size, the number of elements, and the number of nodes. Changing from 20 to 5 in the mesh size doesn't give us an exact correlation for the number of elements or the number of nodes. This is an example of how our CAD geometries might look when we export them from there, normally in STL or step format. We'll get a really fine mesh for the critical areas, the smallest geometry details, and we'll get an average size for the non-solicited areas, the simple geometry. We don't want to have these really long and almost flat triangles because they will affect the convergence of our simulation a lot. So this means we will have to remesh the initial geometries most times. We need to remesh these geometries. Never use an STL mesh directly in Forge if you can avoid it. We'll talk more about how to do this properly in the next slides. One of the first questions we get about meshing is how fine my mesh size should be. And this is a really complicated question to ask. First, the finer the mesh is, the more realistic the result. With a fine mesh in the model, we'll get more realistic results. With a coarse mesh in the model, we'll get a shorter computational time and a minimal storage usage. We have to find a compromise between these two based on how much computation time we can afford and how accurate we want our results to be. This is really hard to calculate. Sometimes reducing the mesh size a little will have a big change, or sometimes changing the mesh size a lot will not have a lot of weight on the results accuracy. This with experience, you will get used to the best mesh sizes for your processes once you try different ones, run some testing and validation, And of course, we can help you with the first trials. It's important to know that the computation time is not directly proportional to the mesh size. Sometimes a finer mesh size can reduce the computational time if it improves the convergence of the simulation. So don't assume that a coarser mesh size will reduce the computation time, because it's not always true. It's true most times. Also, the accuracy of the results, it's not only depending on the mesh size. Sometimes we modify the mesh size and we don't see any change in the accuracy of the results. This might be due to bad material data, the wrong friction files. It's important to keep in mind that there are a whole range of parameters that can affect the accuracy of the results. Okay, that's all for the introduction. Now I'm going to talk about the main parameters we can use in 2D and 3D to create our mesh. In 2D, we have two different windows. We have one for deformable objects and one for rigid dies. In both of them, we'll have a constant mesh size. In the deformable object, will be used to create the external boundary and generate the volume as well. In the rigid die, the contour mesh size will be only used in the external surface of the model. I'm pretty sure most people know those two. I wanted to talk about the other two parameters we have in 2D. The find from factor, it's a factor we use to refine the mesh size in the surface. As you know, in most processes, most of the phenomena happens in the surface of the billet. That's why we want to have a finer mesh there. By default, this value is 2. This means in the external skin of the billet, the mesh will be reduced. The mesh size will be divided by 2. You can see clearly fine boundary of 1 will keep the same mesh size in the skin as in the internal volume. Now, fine boundary of 3 will divide it by 3. And now the precision parameter, it's only available in the rigid dies. This will give us an idea of how precise we are in reading the boundaries of our geometry. The higher the lower the value, the more boundaries we will take into account. You can see the difference between 0.001 and 0.01. You can see it in the corners especially. Okay, that's all for 2D. Now, in 3D, we have more options, obviously. We start with the constant mesh size. This is going to be the average mesh size in our model. It's hard to know the right value here. Again, it will come with experience and getting familiar with your process. It requires some trial and error at the beginning. Once we have defined the constant mesh size, we'll go to the minimum mesh size. Normally, we use 10 times less as the constant mesh size. We divide this number by 10. That's a good rule of thumb. And this is going to be the minimum mesh size in the model. As you know, the mesh is, well, the solver is going to adapt the mesh to the curvature of the model, meaning that if the curvature gets complex, and this value of 8 will be reduced to adapt to this curvature. This effect could go on indefinitely, so we need to set a minimum value, so no matter how complex the curvature is, we'll never go down, we'll never go lower than 0.8. The volumic size factor, it's really similar to the factor we had in 2D, but instead of applying to the surface, it's applied to the volume. A value of 2 means the mesh size inside the volume will be twice as the mesh size will be twice as the mesh size in the surface. So a value higher than 1 will create a coarser mesh inside our piece, and if it's lower than 1, we'll have a finer mesh inside. Now, the three next parameters, size factor, patch angle tolerance, and merge tolerance factor, they are a little more advanced. We'll review them in the next slide. The size factor, it's what we use to regulate the transition between the minimum and the average mesh sizes. As I just said, we'll have different mesh sizes in the model, and we will need intermediate layers to adapt these two mesh sizes. We cannot move directly from 8 to 0.8. We'll need some adaptation in between. The patch angle tolerance is the maximum angle allowed between the normals of two consecutive elements. I'll talk a little more about them in the next slide as well. And the merge tolerance factor will merge nodes that are really close to each other. Okay, we'll review them now. Okay. So the merge tolerance factor, this is an example of what it will do. For example, here, these two nodes are really close to each other, so the solver will merge this node into this one, getting rid of this extra triangle. Same thing here. These two are really close to each other, so these two blue segments will become the red segment here. We use a value of 0.01. It's a percentage value, meaning that if any of the sides of the triangle is 1% of any of the others, the node will be merged. This value has been tested, and we don't recommend to change it. It works in most cases. The patch angle tolerance, again, is going to check the normal between every two consecutive elements. If the angle between those normals is higher than the patch angle tolerance, then an additional element will be added between them, reducing the mesh size and increasing the number of elements in that area. It's a really restrictive, a really powerful tool, so we have to be careful with the values we use. By default, we have a value of 3 degrees, and we recommend to use this in most cases. If you see the curvature is not being properly represented, you can lower this value and get as low as 2, but never lower than 2. I would recommend to test it, changing in really small increments, for example, 2.8, 2.6, 2.4, etc. Now, the size factor is, again, what regulates the transition between different mesh sizes. A value of 1 will give us an abrupt transition between the mesh sizes, and a value close to 0 will give a progressive transition. So the closer we are to 0, the smoother the transition will be. We cannot never use 0. This will give a crash, so please don't use 0 no matter what. And I just want to say that this value has been tested in Transvalor. There's been a lot of testing about it, and the default value, 0.7, works best and is optimal for most cases. So again, I don't recommend to change. Now, I would like to talk a little about the interfaces, the meshing sets we can create in every deformable object, no matter if it's 2D or 3D. These boxes are used to apply different mesh sizes in specific locations of the geometry. For example, if we have an area that requires more detail, we can add a mesh box there to reduce the mesh size. Here we have an example where we need a mesh size of 2.4 in the details in the die, and we want to keep a value of 12 in the outside. In these cases, we need to incorporate a transition, an extra layer to transition from the 12 millimeters mesh size to the 2.4. We cannot directly change from a really high value to a low value. We need transition layers. We recommend a maximum radio of 2. For example, 12, 6, and 3, or 2.4. You can. It's not an exact rule. You can go around it a little, but don't go much higher than that. This is an example for a real case. And I wanted to mention that the order that we use to define the sets is important. The lower a set is, the more restrictive it is. So here we have an example with 4 mesh sizes. If we have areas where they intersect each other, let's look at H3 and H4, H3 and H4. As H4 is the last set, it will override the mesh size imposed by H3. So yeah, keep in mind that the order is important. Normally, we start with the coarser mesh and we end with the finest mesh. Okay, now I would like to talk about mesh quality, starting with the typical defects we see in meshes. Okay, first we have faults. You can see here that with fault we mean when 2 elements are one on top of each other. It looks like this. This extra triangle in red here shouldn't be there. It's a defect probably created by the CAD software, or maybe created by a trimming operation. There are many factors that can create it. A hole, it's just a missing area in a mesh. You can see it here. And the quasi-flat elements, with this we mean really thin triangles or almost flat elements. These are really bad for the convergence of the meshing and the solver in general. We need to avoid them. The more our elements looks like this tetrahedron here, the faster our simulation will. Now, to detect these, we have 4 different results. I will do a demo later, a live demo showing them. They are available before running the computation, so you can check them in the initial results. And they are the faults result. It will show us the faults. Holes will show us the holes in our model. And the surface shape factor, this one is not used that much, and it's really important. It will give us an idea of how close we are to the ideal tetrahedron. This will be a value of 1, and this will be a value close to 0. When we check this result, we want to keep all the triangles higher than 0.4 to guarantee a good quality meshing. Now, the volume shape factor is just this result extrapolated to the volume. So if we were good in the surface shape factor, we should be good in this one too. But keep in mind that this one, we don't have a value. We just want positive values because you can get negative values due to the equation we have here. This is an example with that part. I will show it in the live demo. That's how the holes look. We'll see these red triangles around the hole. These are the faults. We'll review them again in the live demo. Just keep in mind that holes will show us faults as well. So when we see this type of fault, we should interpret this as a hole and not as a fault. And here we have the surface shape factor. You see we have values close to 0 in the areas where we have long triangles. Okay? We want to avoid this with our remeshing. We have values close to 1 in the middle. That's what we want to get, as close as the red parameters as possible. Now, I'm going to talk about the repairing tools we have. to deal with these defects that we have already identified with the results in Forge. We have two types of tools. We have global repair tools and local repair tools. I'm not going to explain all of them because I don't have time. I'm going to explain the ones I use the most, and I think they are the most useful tools for everybody. All of these are, most of them are really advanced, the global repair tools, and you can find a lot of information about them in the online help if you need or if you want to know more about them. The one I use the most, it's called Unfold Mesh. And what this does is it will scan the whole mesh in your model, and it will remove all the faults it finds. The issues with this is that sometimes we have too many faults and the tool can get overwhelmed by all those faults. Or sometimes the faults are removed drastically, and you can even see sometimes some holes in the model after removing the faults. So after running this tool, even if the faults are removed, you should double check your geometry to make sure it works properly. It's still a tool that is being improved every version, so be a little careful when you use it. Normally, what we do though, is use the local repair. Only if we have a small number of defects. If we have hundreds of defects, we have to try the global tool or try to do a better export in our CAD software. On the local repair, I mainly use the fill holes to get rid of the holes in our model. In this tool, you have to select one of the edges in the hole, and the solver will automatically populate that with triangles. Merge nodes, as you can see in this picture, will delete the extra fold, moving the first node to the second node. This is the best way to remove faults because you have a lot of control over it. I'll show you in the live demo now. But this is normally more accurate than using the global repair tool. It just takes some time if you have many faults, but it's perfect to fix one or two faults that you might get from your CAD software. Now I'm going to go ahead and show you a real demo of this. This is a die, the die I showed you before in the results. First, I'm going to go over the results really quick. Again, I don't have results yet, so I haven't run my model. I'm still in the preprocessor phase. First, if we run the holes, we'll see where the hole is right there. Faults, we see clearly two of them. If you cannot find them because they are really small, you can use filtering and just increase this value. So it isolates the faults. Then once the filtering has been applied, you can reposition and it will take you exactly where the fault is. Once this is done, you can deactivate the filtering and you will have a view of your fault. That's what we normally do when they are really small and we cannot find them easily. Now the surface shape factor, you can see it here. It's really low, so we need to remesh the part to improve this. Okay, that's how you visualize the results I mentioned. Now I'm going to show you the repair tools. They are in meshing, global repair, and local repair. I'll start with the local repair and fill holes. I'm going to visualize the result, and I'm going to go back to the meshing, local repair, fill holes. What we have to do here is select one of the edges of the fault. I have select those two nodes, and I'm going to confirm. As you see, this element has been created and the fold and the hole has been filled. Once we don't have holes in our model, we should see our part in green and we should see a 0 here. That's an indication of a clean model. Now I'm going to change the result to false. If we see our part in blue, it means there's a fault somewhere. We just cannot see it easily. To guarantee we don't have faults, we should see a green part and only a 0 on the legend. Okay, so now I'm going to change the visualization to surface mesh. We can see this triangle shouldn't be there. It's an extra triangle. It's a fault. So I'm going to go to meshing, local repair, merge nodes. What I'm going to do is move this node to this node. Select the first node and select the second node. Confirm. And the fault has been removed. And we have a clean model. Now, if I come to the same model, I'm visualizing the faults again, and I try the global repair and fault mesh to get rid of that fault. This is a good example to show what can happen. The fault is removed, but as you see, it hasn't been done as accurate as you can do it with the local repair tool and with a human being doing it. It has removed the wrong part of the fault and it has made a small hole in the model. So be careful with this effect when you use the global repair and fault mesh. Okay, that's all for the quick live demo. We're going to move now to the Remeshing tab. This is a new tab that has been implemented in the last versions of Forge, and it will let us define the trigger mode for the remeshing and how the mesh adapts once the remeshing starts. First, let's talk about the initialization of the remeshing. Here we see that we can activate or deactivate the remeshing. It's possible to deactivate it. It's not recommended because the mesh is going to degenerate in most simulations, but it's an option. And by default, you'll have the remeshing on the formation. Oh, sorry, I thought I lost the audio. Okay. By default, we have remeshing on the formation. What this will do is it will start the remeshing when the deformation in the part is bigger than this number. It's related to how much the elements can deform before triggering the remeshing. Again, this value has been tested and we don't recommend to change it. In previous versions of Forge, the remeshing on period was the default for some processes. This means every 20 increments, for example, or by default, to every 20 increments calculated, we will remesh the part, no matter if it has been deformed or not checking any of the results on it. This meant a waste of time sometimes because we were remeshing something that didn't need to be remeshed. So now we use the remeshing deformation as the default mode, and the computational time has been highly improved thanks to this. So here you don't have to change anything in most cases. Remeshing is activated by default and remeshing on the formation is activated by default. Now, for the mesh adaptation, this is the second tab or the second option in the remeshing tab. Here we have by default the standard mode as the remeshing mode. Again, this is without changing anything. All of it is defined by default. The standard mode will take into account mainly the contact, the curvature, and the volume as the factors to modify the mesh entered by the user. The final mesh will be the mesh entered by the user multiplied by the minimum of these factors. Contact and curvature. Contact is related to the billet being in contact with any rigid die. If this happens, we will reduce the mesh to adapt it, to lower it and get more detail in the contact areas. There's always a lot of things happening there, and we want a fine mesh in the contact area always. Curvature is related to the curvature of the part of the billet. When we have complex curvature, we want to reduce the mesh as well. And volume, it's related with the volumic side factor. It means we will use a coarser mesh in the volume than in the surface, in the external surface, because again, most of the phenomena is happening in the surface and we don't need a fine mesh in the volume. The other modes, no mesh adaptation, it means that the solver will use the mesh specified by the user. It will not apply these factors. We don't recommend this. We recommend the standard as it improves the computational time and it doesn't affect the results in most cases. Field adaptation will allow us to add additional factors to the ones I presented for the standard. For example, we could remesh based on the gradients for the strain rate or the equivalent stress. This means we will add more nodes where the gradients are higher for these parameters. This is an option. If we are really interested in this, we can add it to our mesh adaptations during the remeshing. Finally, I want to talk about the automatic size and node refinement. I want to explain what this is because I get a lot of questions about it. Automatic size will take into account not the curvature of the deformable object, but the curvature coming from the tool that is going to deform it. This means when the tool is getting closer to our die, the mesh size will be reduced in that area, preparing for the contact and the deformation. Node refinement will avoid getting coarser mesh in the model due to these factors I mentioned. This means the factor can reduce the mesh size entered by the user when there's contact or curvature, but it cannot be it cannot get coarser. For example, inside the volume, we normally multiply the size by 2, as I mentioned before. If we activate node refinement, this will not happen. The maximum factor we can multiply our mesh will be 1, so it will never get higher than the user. Finally, I want to make a comment about the progress we have done in the mesh adaptation in the last version in Forge 3.0, especially in the contact zones when we have fillets on the tool. Okay, here you can see a huge change in the mesh adaptation. This is an example provided by a customer. And in the next slide, this is done automatically, and it has been implemented again in the last version. So I recommend everybody to update to the latest version. Changes. This is another example, before and after, for a crankshaft. You can see the mesh size in the contact areas has been highly improved, especially in the change of curvature. And in this specific example, it meant it reduced the computational time enormously. It was almost half of the time. So please, everybody, update to the latest version to take advantage of this, especially if your parts look like this. And this is all for today. I hope everybody got something from the webinar. Again, we are taking any feedback that you can provide to select new topics and to add any content to this webinar series. I want to remind everybody that we have the online help. It's updated almost weekly. with all the new features applied in any of the software. Also, for the webinar done today, you can review Chapter 3 in the reference documentation. Has a lot of information about all the topics I have described. And lastly, I want to remind everybody that we are offering online trainings now that we are all working from home, and they are completely customizable. So please contact us to our support email for more information about it. This is all. If anybody has any questions, I would love to answer them now.
Yeah, thank you, Sergio. If anybody has a question, please use the chat and we'll review your question. While you're doing that, I'd like to thank you, everybody, for being here. Today, I'm very sorry. It seemed that there were some issues with connections sent, so everybody could join afterwards. Anyway, I'm sorry about that. We'll make sure that next time doesn't happen. So also we have recorded this webinar as all the webinar we do. They will be available in the member area. That is through www.translaterusa.com, which is our website, and then you have the members tab. If you haven't signed up yet, please do so, and we'll accept your request shortly after. Okay? We'll communicate when the video is available, right? So you'll receive an email either later today or on Monday with a link just announcing that you have the video is uploaded on the website. So we are still working on the topic for next webinar. We take into account all your input and do our best to include them in our webinar. Our next webinar will be held in 2 weeks. All right. So now we'll start keeping this pace, this 2-week pace, and it'll still be on Friday at 10 a.m. Central. We'll send the email announcing the new topic at the beginning of the week. The webinar is there. Okay. In the meantime, do not hesitate to contact us should you have any questions. I don't see any question in the chat. So again, if you have any question, you can send us an email at regular tech support email, which is support@translateramerica.com. Thank you again, first Sergio, for this excellent presentation, and thank you all for joining today. Stay tuned, and thank you again for joining. All right, we'll be in touch very soon. Thank you. Bye.